This is the new work that I published with my colleague Guillermo a few weeks ago, and happy to present it here. So on this talk, I'll try to give like a quick overview of techniques and maybe keep it a little bit more high level so that we can discuss some implications of this. But I'm more than happy to dive into deeper stuff later if you want, and we can spend some time on it. So as the name itself says, it's based on previous work that's called Ligero, I don't know, like you can choose. And thus you can choose how you call our paper based on how you pronounce Ligero. So today we'll just go quickly through what Ligero gives us, and just very briefly with some seemingly very stupid observations, which will then build up to what we call Ligerito now. So not sure how familiar you are with this stuff, but in general, Ligero is a really nice paper, very useful, and just on a very abstract way, it allows prover to commit to some matrix by first encoding it, and then it can prove that what he encoded is uniquely close, is close to some unique matrix. It makes a lot of sense when you work with coding theory, when you work with codes, when you want to test if something is close to code words, etc. For us, it will be interesting in a very seemingly non-related way. So you can actually represent the evaluations of the polynomial you want to commit as these matrices, then encode them and do a lot of tricks to get a polynomial commitment scheme. So since you're on this stage, I guess you know that once you have a good polynomial commitment scheme, you can get snarks, ZK snarks, and that's kind of the backbone of every modern snark. Okay, so I'm not going to go into details, but essentially, especially for multilinear polynomials, they have very nice tensor structures, so you can very nicely pack them into these matrices or hypercubes and like partially evaluate them, etc., etc. But let's keep it high level. So before we go into what we do, let's just look into this very complex picture of how Ligero works. So we have some unique matrix X tilde, and we encode its columns with any code you want. And then what prover does, it commits to rows of this matrix via Merkle tree. Or like any other vector commitment, but practically it's always Merkle tree. And then what happens next is that verifier sends some randomness, as we always do in snarks, and prover sends the matrix vector product of the matrix it has in its head, or what he claims to have, with this randomness. So after sending this vector we call YR, that is in the red, I don't have a pointer, sorry for that, then the protocol is very simple. It just checks some inner products between random rows of this matrix with the vector that verifier sent. So if you remember, we said that the rows are committed via Merkle tree, so prover can open these rows and verifier would just check a bunch of inner products with some vectors. So it's very simple but extremely powerful protocol. The main advantage is that it's super fast. So if you use efficient code, you encode these columns very efficiently, you commit to rows, it's just like a bunch of hashes, which are very, very fast, and you just do some random linear combinations, which is essentially also very fast on modern hardware, and very important fact that we also use a lot in our work is that the most expensive parts of this computation are fully parallelizable. So if you want to work with some binary field extension, say 2 to the 32, you can commit to very large polynomials on like your normal laptops with just like around 1 second. So it's quite fast. I would say a problem is that proofs tend to be large. And when we say snark, we want to have small proofs and efficient verifiers. So, for example, for above mentioned polynomial of 2 to the 24, the proof size gets to be like, for optimal dimensions and packing, you get around 825 kilobytes, which can be large for the modern snarks we want to achieve. Okay, so you can actually see some very stupid observations, and this paper somehow makes sense, and observations are seemingly very simple. So you can do a lot of smart stuff if you want to like optimize this proof size. So you remember we said we have this matrix, so like you can have a very few columns, so very like shrink matrix, and then these rows tend to be very small, and you reduce proof size. But then you have like another message called YR that then grows larger. So it's kind of, you cannot optimize for both. And the main observation of our paper is that you can actually merge the sumjack protocol, which is a very, very fundamental protocol in a lot of multilinear snark stuff, with Ligero. And this is kind of the core fundamental thing that we do in our paper. And you have to be like smart how you combine randomness, which rounds, how you fold, but that's maybe for like more detailed and more mathy talk. So the core idea is, if you have these tensor structures of your multilinear polynomials, when you pack them in these matrices and you do these matrix vector products, they are equal to partial evaluations of your polynomial. So what you can do is in a few rounds, you can actually partially evaluate your polynomial until the very end, where you get the full evaluation of your polynomial. And having the polynomial evaluation in random point gives you like PCS, which you can use again to build very efficient snarks. Okay, so you need to compute like a lot of inner products, as we saw on a very far side, and the core idea is that you can actually delegate that to the untrusted prover via some check and combine everything and magically get a very nice. So in like pure Ligero, what happens is that the prover just sends this YR, and then it just uses a few spots of this YR vector. So the whole idea, and again, you can see this pattern happening in a lot of snarks. How we build them is you essentially put all of that cost back to the prover to make efficient verifier and minimize all the work that he needs to do and the stuff that it has to see. So, right, now if you have a sumcheck and Ligero, you also get just inner products for free. So it's not just that you have a PCS, but you also have an inner product for free. And then if you have an inner product, you can also build different kind of snarks. So it kind of all makes sense at a very high level. Okay, so then what people tend to do when they want to get like succinct actual snarks and like very small proofs, that's like recursive wrapping. So you have like something, you prove something, you take that proof, and then you also prove that you have seen the valid proof, so to say. So the idea here is very similar. What you can actually do, you can verify Ligero within self, and then recurse that many times until you get something very succinct. Okay, so yeah, this meme, you can just do Ligero in Ligero by doing Ligero itself. Very weird. Okay, and then that's why we call it actually Ligerito. So you start doing the same thing. You have some unique matrix, you commit to the columns of this matrix by first encoding the columns and then sending it via, again, same Merkle tree, you get some randomness, and you send YR. Okay, so what's the difference? Now we don't want to send YR because that's the whole problem of just using the normal Ligero, and that's where the proof size explodes. So what you can do, instead of sending it, you again just commit to that YR, and then just imagine that somehow magically recursion will solve this for you. So you can just proceed to the next round and prove something on that YR. And you use the sumtrack protocol to somehow glue all these intermediate steps. At the very end, you can have a very easy inductive proof that everything was correct and everything made sense. So Ligerito then becomes just like a lot of, or I would say a few Ligero things, which are together glued with one big sumtrack protocol that is also partially being run in parallel. The mechanics of it are a bit complex until you get really deep into it. So it's sounds stupid, but actually it's very powerful, okay? So after you solve some convex optimization problems, you can compute this optimal dimensions. I'm not gonna go into there now, but for practically everything we need now, which is around 2 to the 30 coefficients polynomials for larger ZK VMs, you just do 3 or 4 these recursive iterations, which makes it very efficient practically. So, I would say that around 90, but even more % of the time that you spend on prover is in this first step that you would actually do the normal Ligero. So you pay extremely little on the prover side, on the computation part, but you actually get a succinct argument, which is, again, why we need snarks, right? So just to show you some numbers, so we'll just compare to Ligero. We can compare to other PCS, but that's not gonna go there now. But in general, the asymptotics were square n, where we run in log n square over log n. Doesn't matter, but just look into these numbers. It's way better. So for example, for 2 to the 28, you have extremely small proofs, which are just 360 kilobytes. Okay, that's not all. The implementation I have is written in only a few weeks, and I was running it on this laptop, so very personal MacBook without GPUs, without some crazy amount of cores, etc. Just 8 cores, and the numbers are insane. For example, you can get 2 to the 30 polynomials in just 80 seconds on a personal computer. So if you remember the beginning of the talk, every single part of this computation is fully parallelizable, and it has very low memory pressure on the prover. So essentially this linearly scales with the amount of cores you have. So if you have 64 cores, you can actually divide these numbers by 8. So I would say with more engineering and more hardware people who are not me, you can probably do 2 to the 30 on a in just a few seconds on your personal machine, which is insane. And instead of having a bunch of megabytes, it's very practical. You get for 2 to the 30 under half a megabyte of the proof size. If you're more familiar with like phones and stuff, if you're smart and like if you manage memory correctly, you can get like a very huge proof sizes, and very huge polynomials on your phones, which is again something that we were not sure was possible before this. So the implementation is open sourced on our GitHub. You can also find the link to the paper on this QR code. So, right, like, I think this might be like a very big news for Snarks. We really, I think, unlock a lot of potential, what people wanted to do for many years. And you can have phones and computers being disprovers, and since everything is like parallelizable and so independent, you can have like a lot of other very light verifiers who can just sample parts of this proof, and it gives you like a very complex data availability schemes, which also means that we might even redesign how our like today's blockchains are working. You can achieve a lot by just having the phones being like a good enough to do either like some proofs or just to verify a chunks of these proofs. So it's like field agnostic, but it's extremely like efficient on binary fields, and we know that our computers are built for working over binary fields, which I think it makes it even stronger. There are other like other theoretical aspects of this, which I'm not gonna go there, but there is also some stuff called code switching, which this paper gives us implicitly. So essentially, at any round you want, you can use a different code, which is also like completely different thematics, but you can do a very smart stuff to like have even faster provers than what I showed, because I was doing it like on a Reed-Solomon codes with a constant rate. You can change rates over the rounds of faults, you can change codes, you can do a lot of smart stuff depending on what you need. And yeah, having 2 to the 30 polynomials being run on your computers should definitely be something very huge that we hope to get in the next following years. My time is over, right? Yeah.
There is a question.
Thanks for the presentation. I will definitely check out the paper. You also showed some some optimization ideas regarding the size of matrices and rows and columns, and also you at the final stage you said it's possible to use different fields in different in steps. So I'm wondering, would
no different fields. Like you have one field, but you can use different codes and different rates
different codes,
per
yeah.
step. Yeah.
I just thought, like, at least in the opening round, would it help to use a smaller subfield?
Yeah, sure. Yeah. So that's what we do. You can have like your arithmetization of a very tiny field, and then anyway in the later rounds you have to use the big enough field extension, right?
Yeah, thank you.
So yeah, that's how we do it. And the first round is the biggest one where you have the smaller. Yeah, that's right.